Assalamualaikum warahmatullahi wabarakatuh. And hello, my name is Muhammad Amir Rabi Rasman. I'm from 1A3. This is subject ECW422. This is about fluid mechanics. We are presenting about hydrostatic force on them. And this is my friend. Her name is Aiman Mirza and Shahrizan. And this one is Aiman. Say hi, Aiman. Bye-bye. We will begin on introduction of hydrostatic force on dam. In civil engineering, dam is a massive hydraulic structure to build across a river or a stream catering a reservoir. In dam, floodgates are acting as a control valve to hold back water and release it when it reaches certain level. This structure made to experience hydrostatic force when it withstand force exerted by stationary water and increase with water depth that owns the dam. Consequently, if a water gate cannot properly function, it will cause severe flooding and landslide, which is case on Aceh right now.
As for that, the objective of our project is to design and construct a small-scale vertical dam as to test its behavior under 3 different water heights, to examine the hydrostatic forces acting on the dam, and lastly, to observe the structural responses of the water gate under different water heights.
One of the problems regarding water gate at dam is reliability of operation, where certain gates would only be used once in almost 100 years during flood event, thus would result in corrosion and power failure. Furthermore, debris blockage would happen to water gate as during floods, the river carries trees and sediments, making the gates jam and water rising uncontrollably in reservoir.
Today, we are looking at why floodgates behave the way they do when water level rise. It all starts with hydrostatic force. When water is stationary, it's still working. It exerts a constant push on any surface it touches. But here's the catch. That push isn't uniform. Because of gravity, the deeper you go, the higher the pressure gets. We define the pressure at any given depth with a simple relationship. That is, pressure equals to rho GH. Basically, the pressure P is the result of the water density, gravity, and how far down you are. The deeper the water, the harder it pushes. When we apply this to a submerged gate, we need to find the total hydrostatic force, F. To do this, we don't look at the bottom, we look at the centroid, the geometric center of the submerged area. The formula is F equals to rho GAHG, where A is the area and HG is the depth of that center point. This tells us how much total weight is pushing against the gate. Now, here is the most important part. The force doesn't actually hit the gate at the center, because the pressure is much stronger at the bottom than at the top. The average point of impact, called the center of pressure, HCP, is always lower than the centroid. We calculate its location like this: HCP equals to HG plus I over HGA. This offset is why gates often feel like they are being kicked at the bottom rather than pushed in the middle. Finally, we have the moment. Since the gate is usually on a hinge at the bottom, this force creates a rotation. The moment is simply the force multiplied by the distance to the hinge. As the water rises, the force gets bigger and the center of pressure shifts. These two factors combined explain why a gate might stay still at the low levels, but swings open with massive power once the water reaches at a certain height.
Moving on to case problem. In case 1, where there is no water in dam, the water gate will not be open due to no pressure detected and the water not surpassing the limit of the height of dam. For case 2, where the low water level, the water gate will also not be open, as the water not surpassing the pressure limit, although there is a little pressure detected. For case 3, where the water is at maximum level, the pressure of the water will surpass the pressure limit. opening the water gate and releasing the water inside of the game. This is because the water is above the height limit of the dam. It will make the dam open the gates and make it open to from the flash flood to begin.
So moving on to the discussion, in case 1, it is an empty dam where both pressure and force is zero. Thus, no fluid to exert a lot and the only force acting is the gravitational force. The control systems detects no input, so the gate remains closed.
For case 2, there is slightly high due to low water height, so it results in low pressure. There is little hydrostatic force at the base of the gate, although the gate remains closed but the system fills the water but dims itself.
For case 3, the water level is at maximum, which results in high pressure and hydrostatic force. The force will act on the center of the pressure, which located at 1/3 the height from the bottom, creating powerful moment that tries to tilt the gate open. Once the force exceeds the limit, the gate will open, preventing the dam from overflowing or the structure to crack under immense load.
So, I will talk about SDG 9 connection. This dam watergate project is directly linked to Sustainable Development Goal 9, which focuses on building resilient and sustainable infrastructure. Watergate is crucial in managing flood by controlling water levels and preventing uncontrolled flooding that can damage the people and infrastructure nearby. By analyzing the watergate under 3 cases, these projects demonstrate the importance of infrastructure resilience, where civil engineering structure need to continue functioning under extreme conditions. In addition, the prototype is constructed using recycled material, which is parallel with sustainable material use and shows how effective engineering solutions can be achieved using minimal resources. Thus, understanding it will be lead to engineering making safer, more resilient and sustainable dam infrastructure design. So to conclude, this project successfully demonstrates the application of hydrostatic theory to practical civil engineering structure. The experimental observation verifies that hydrostatic force and pressure increase with water depth, which is aligned with fluid mechanics principles. Despite increasing hydrostatic force at higher water levels, the watergate remains functionable and operates well, indicating its structural effectiveness. As a matter of fact, did you guys know that humans are not the only one that construct them? Beaver also has to provide safety from predators via underwater entrance and food storing for winter.
You guys must think that there's no calculation, right? But there is there is two calculations, and the difference between these two is only in their height, which is for case 2 it is 0.03 and for case 3 it is 0.05. What you need to do is to first find the area and then find the centroid depth and the second moment of area using I equals to bh power of cube over 12, and then you need to find the center of pressure using hp equals to hg plus ig over hg multiply with a, and then you need to find the hydrostatic force using F equals to rho GHA, and then you need to find the moment, and that is it. Both cases are using the same equation but difference in height. I hope you guys can understand.